In the fourth video on polars, I'm going to talk first about the area between two polar curves, and we'll work an example, and then I'm going to talk about arc length. So much like what we do in rectangulars, if we want to find the area between two curves, we can see the blue curve is R1 and the green curve is R2, and we're going between those two angles in yellow, alpha and beta. So if we want the area between the green and the blue curve, we're going to find the area of between the blue curve and the pole in between those two yellow curves, which we know from what we've talked about before would be 1/2 the integral from alpha to beta of r1 squared, and that would be d theta. And then we would subtract from that the area between the green curve and the pole, which would be 1/2 from alpha to beta of r2 squared d theta. And so in what we get, much like what we see sort of with rectangular, is we can simplify that if we like and just call it the integral from alpha to beta of r1 squared minus r2 squared d theta. So that's how we're going to find the area between two curves. So let's look at an example of this, and you're going to need your graphing calculator. I think that will help see what's going on here. We're going to find the area between let me say the area of the region. Sorry about that. The region that lies inside the circle, that lies inside the circle given by r equals 1, and outside the cardioid, and I'll give you that equation also. The cardioid given by r equals 1 minus cosine theta. So you can do this on your calculator and get a nice picture for it. The t values, or the theta values rather, so the theta values will go from 0 to 2 pi, and you can set your x min and x max to go from -3 to 3, and your y min and y max to go from -2 to 2, and I'll try to show you kind of what you should be looking at. So if this is our axis, I'll do the circle in blue. So here is our circle of radius 1, and our cardioid is going to go something like that, more or less. You have to use your imagination there. We are trying to find the region inside the circle, but outside the cardioid, so we're talking about this region in yellow right there. So what we need to do that is we need to find those points of intersection between the two curves, and we probably have a pretty good idea what that is just looking at the graph, but we can set our R1 equal to R2. That is, we're going to set our 1, which is the circle, equal to the 1 minus cosine theta, which is our second curve. So we can subtract the 1's and get cosine theta is equal to 0. I'm going to add the cosine to the left side just to make it positive. It doesn't really matter. Now, here we have to put some thought into where is cosine theta equal to 0, and we can see there that certainly that would be pi over 2 and 3 pi over 2, and we could keep going on and on. But we want to look at our graph and know that we want this region that's going to be kind of in between here. So as we go from those points of intersection, we want to sweep like Doppler radar in a continuous motion. So that means we're going to pick negative pi over 2 as one point of intersection, that one right there, and pi over 2 as the other point of intersection there, so that we can integrate like we've shown there on that continuous interval. So that means we're going to get for our area that it's going to be 1/2 that we can pull out of our integral. We're going to go, our limits are going to go from negative pi over 2 to positive pi over 2. And we're going to go with our first curve squared, so that's the 1 squared, the circle, minus the inside curve, or the second curve, which is our 1 minus cosine theta, that quantity squared, and that is going to be then a d theta. And if you punch that into your calculator, I believe you should get 1.215. And that's fine, and that's a great way to do it. Just alternatively, it would be reasonable and correct and acceptable if you thought of that, if you recognize that first area between the blue curve and from negative pi over 2 to pi over 2 is really just a semicircle. And so you could have done 1/2 the pi r squared for the blue, the region between the blue and the x-axis, or the y-axis rather, and then just subtract off the cardioid, the 1 minus cosine theta squared d theta. That would have worked well as also. Okay, so what I want to do now is let's talk about arc length. And so what I want to try to do here, arc length and polar, is going to kind of give us our third formula for arc length. If you remember in rectangular, we already did this, rectangular. We said we were going to go from, say, a to b, and we had the square root of 1 plus f prime of x squared dx. And then what we're more interested in building off here is in parametrics. What we said for arc length is that our length is going to be the integral from, and we said t sub 1, some time value to another, and we were going to go just the square root of dx dt squared plus the dy dt squared dt. Oops, let me do that a little bit better. So if you want, it's going to be the dx dt squared plus dy dt squared. Now, what we're going to try to show here is in polars, we're going to first go from the parametrics to changing our parameter from being t's to being our thetas. So we're going to go from alpha to beta, the angles, and we're going to get our square root of, and then we're going to call it dx d theta squared plus dy d theta squared d theta. So we're going to change our parameter, and then hopefully we can get to our final formula, which is what we want to get, is from alpha to beta, and we're going to, I hope we can show this is going to be r squared plus dr d theta squared, dr d theta squared d theta. So let's see if we can do that. So first we're going to remember that our parameterization, or that is, we think of x as a parametric as being r cosine theta. And remember that r is a function of theta, and so we need then to get dx d theta. And so dx d theta is going to be a product rule. So we're going to get the first r times the derivative of cosine theta, which is going to be a negative sine theta, plus the second cosine theta times the derivative of r, but remember r is some function of theta. Think rose curve, limacone, something like that. So we're going to call that dr d theta. And we'll do a little cleanup and just bring that negative in front of the first one. So we have negative r sine theta plus the cosine of theta times dr d theta. So that's our dx d theta. We're going to need dx d theta squared. So I'm going to square that whole thing out here. That is, I'm going to take that whole thing out and square it. And so we're going to get the first one squared. That's going to be r squared sine squared theta plus twice the product. So that's going to be a minus 2 r sine theta cosine theta times dr d theta. There's our twice the product, plus the second one squared, which is going to be a cosine squared theta times dr d theta squared. My thetas keep looking like t's. Okay, so we're going to save that for a moment. Let's come take a look at y, which is going to be our sine of theta, and that means, oops, let me see if I can bring my eraser up here. Okay, so from there we're going to get dy d theta. So here's another product rule. The first r times the derivative of the second cosine theta plus the second sine theta times the derivative of the first, which is a dr d theta. So again, we're going to get dy d theta squared. So dy d theta squared is again going to be the first one squared, r squared cosine squared theta plus twice the product, which is going to be a 2r cosine theta sine theta dr d theta plus the second one squared, which is going to be a sine squared theta times dr d theta squared. Okay, now it's kind of nice that these are kind of lining up here a little bit. So the inside of our formula for arc length, we're going to need dx d theta squared plus the dy d theta squared. So let's see if we can see what that's going to look like. We're going to get the r squared sine squared theta plus an r squared cosine squared theta. I'm going to write that in, I'm going to factor out the r squared. So that's going to be r squared times sine squared theta plus cosine squared theta. Oh, that was really nice. We can also see that the minus 2r sine theta cosine theta dr d theta is going to get added to the 2r cosine theta sine theta dr d theta. Well, they're going to cancel each other out. Better still. And then we're going to, in a similar fashion, we're going to get the cosine squared dr d theta squared plus a sine squared dr d theta squared. So I'm going to factor out that dr d theta squared times, and that's going to multiply then cosine squared theta plus sine squared theta, which is going to be convenient as well. So we see our favorite trig identity emerging in both those cases, and so we're going to end up with r squared times 1 plus dr d theta squared times 1, which is exactly what we want to get inside that radical, which is there. So we have shown that our arc length formula in polars is going to be the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. So there are, in fact, 3 now different formulas that you're going to have to know for arc length, depending on if we are in rectangular, parametrics, or polars. All right, let's do one crazy example with arc length. And this is, I think I have an example, or do I? Nope, I guess not. So we'll go ahead and wrap it up. You can try the homework, and if you get stuck, we can talk about these in our Zoom meetings.